So, good morning all. We'll start our fourth module. First topic is transmission line. So, what is transmission line? In this figure, you can see two different transmission lines. This one and this one. This one is a two parallel conducting wire separated by a dielectric medium. This is one type of transmission line, and this is a coaxial cable. There is an inner coaxial cable and an outer coaxial cable. This is also another type of transmission line. And you can see here these two parallel conducting wires are connected through an energy source. So what happens here is there will be a power transfer between these two parallel conductors. Similarly, here also the power gets transmitted from the inner coaxial cable to the outer coaxial cable through this energy source. Okay, so that is transmission line. Transmission line is simply defined as two parallel conductors separated by a dielectric medium, somewhat similar to a capacitor in our normal circuit, right? So in the next section we will see the parameters of a transmission line, that is the primary constant or characteristic constants of transmission line, or otherwise known as line parameters. Now here you can see two parallel conductors. These are two parallel conductors which is separated by a dielectric medium. Now here what I have done is I have divided these two conductors into small segments. You can see the dotted line. So why I have done so is to reduce the transit time effect. So then what is transit time effect? Okay, now we can take a simple circuit. This is the generator side and this is the load side. Okay, generator, or otherwise you can call it as source, this one. Okay, so most commonly we use the term generator instead of source in transmission line. Here I have taken 2 points, here A dash B dash and here AB, which is separated by a distance L, and here I have drawn a sinusoidal wave whose time period is capital T. So this wave is generated by the source. Now I will read out this statement. Let us assume an instant voltage of Vp has to be transmitted from A dash to B dash. That means I am assuming that this voltage, I am taking an instant voltage Vp as an example. Okay, just as an example. This Vp has to be transmitted from A dash to B dash. The time taken by Vp to reach B dash is T equals L by V, that is equal to Tr. So you know what is time? Time is equal to distance by velocity, that is written here. T is equal to L by V, which is equal to Tr. This Tr represents the transit time. So the time taken by this voltage Vp to travel from A dash to B dash is your transit time. Okay. Now we know once B dash reaches at a potential of Vp, the potential across A dash changes, right? Now A dash is not at Vp potential. It has changed because now B dash is at Vp potential. So now what will be the voltage across A dash? That I am taking it as an example. As an example, I am taking as VQ. Okay. So right now the voltage across A dash is VQ. Let it be VQ. Now there is a potential difference between A dash and B dash, right? But now you know that is B dash is at Vp potential and A dash is at VQ potential. So there is a potential difference, and this potential difference is known as transit time effect. Now in order to keep potential difference at 0, the transit time should be make 0. Okay. So if you want to make the potential difference between these 2 points 0, then what you have to do, you have to make this transit time equal to 0, which can be achieved if capital T is much greater than TR. What is capital T? Capital T is the time period of this wave. So in order to keep the potential difference at 0, transit time should be made 0, which can be achieved if capital T is much greater than TR. Then what is T? 1 by F, much greater than L by V. Then this V is taken here, V by F is much greater than L. So finally we can conclude that if you want to prevent transit time effect, then the wavelength of electromagnetic wave should be much greater than the distance between any 2 points in the circuit. So clear? That is transit time effect. Repeat, that is, initially I have taken the voltage across A dash as Vp. Now this voltage travels from A dash to B dash. At that time what happens? The voltage across A dash changes, and that is taken as Vq as an example, just as an example. So A dash and B dash are at entirely different potential, and if you want to make potential difference equal to 0, then you have to follow this condition that lambda is much greater than L. Next, why transit time comes into picture in high frequency circuit? In normal circuit, we are dealing with a maximum of 330 volt 50 Hz supply voltage. But in transmission line, we are dealing with a frequency in the range of gigahertz, right? So what happens here? In the case of normal circuit, here I have taken 2 points, AB and A dash B dash. So the frequency is also given 50 Hz. So what is T? 1 by 50, that is nearly 0.02 second. Similarly, in this case, the T is 10 raised to minus 9, because I have taken frequency as 1 gigahertz. So 10 raised to minus 9. So what do you understood by 10 raised to minus 9? 10 raised to minus 9 means that particular signal, the signal which is traveling from A, B to A dash B dash will be changing very fast. It will be very fast. It will be switching from one voltage to other very fast. While in this case the change will be very slow, because very slow in the sense compared to the transmission line, here it will be very slow. So the potential difference will also be changed. The change in potential difference will be comparatively low in this case compared to this case. Here the waveform will be changing from point to point very slowly compared to this case. So the change in potential difference will also be comparatively less here compared to this case. That is why transit time effect is of much importance in high frequency transmission line. Okay. So coming back to the line parameters of transmission line, to reduce the transit time effect, the parallel transmission wires are divided into small segments, out of which I am taking a small segment, this one, whose length is del Z. Okay. Now if you magnify that small portion, you can see actually these two are parallel conducting wires. So you know wire behaves as a resistance, right? That is drawn here. The resistive behavior of wire is shown here. Similarly, you know at high frequency this wire will behave as inductance, right? XL is equal to L omega. So at high frequency, this wire behaves as inductance. That is drawn here. So the wire possesses, conducting wire possesses a resistive behavior as well as a inductive behavior. Now I told you that these are two parallel conducting wires separated by a dielectric medium. That means it acts as a capacitor. That is drawn across the two arm. Here the capacitor. This is here. This is the upper arm and this is the lower arm. This one. This right. This is this one. This line corresponds to this line, and this one corresponds to this wire. Okay. So the two wires are separated by a dielectric medium. That means these two wires have a capacitive behavior, which is drawn here. Now at high frequency, there are chances of charge leakage between these two wires. So there will be a conductance between these two wires, which is represented as G. So this is the equivalent circuit of a transmission line. Okay. So here I have drawn the equivalent circuit with respect to one arm only. Here you can see I have drawn it with respect to the two parallel wires. So you can draw it as L1 R1, L2 R2, G and C. Both are the same. Okay, here I haven't drawn the lower part. That's all. So I repeat, when you zoom this smaller portion, you can see the wire will be having a resistive nature as well as inductive nature. Then between them, between the two wires, it will be having a capacitive nature and a conductive nature. So that is written here. Any wire has resistance. At high frequency, wire behave as an inductor. Since transmission line is two parallel wires separated by dielectric, it acts as capacitance. Between two wires at high frequency, there may be chances of charge leakage, which constitutes a conductance. Hope it is clear how the equivalent circuit is drawn. Now one more point that you have to keep in mind is here the unit of L is not Henry, it is Henry per meter. Capacitance is farad per meter, resistance is ohm per meter, and conductance is mho per meter. Till now what you have studied is the unit of inductance is Henry, capacitance is farad, resistance is ohm, so and so, right? But here it is per meter. Why so? Because here we are measuring the inductance, capacitance, resistance and conductance with respect to a small region whose length is del Z. That is why the unit is Henry per meter, farad per meter, ohm per meter and mho per meter. Okay, because here we are measuring, here we have drawn the equivalent circuit of the wire with respect to the small distance del Z. Clear? That is why that meter is there in your unit. In the next video we will see transmission line equation.